Let's start the slideshow from the current slide. And let me go over the couple of announcements. Nothing too major. Most of what you've probably heard. This afternoon at 4 o'clock, excuse me, sorry, our volleyball team will be taking on Coastal Alabama South, and that will be on the Birmingham West Campus, 4 o'clock this afternoon, Arthur Short's Fine Arts Building, which is also the gymnasium. And then that's at 4. At 7, it's a doubleheader because they will be taking on Wallace State Selma at 7 o'clock this evening. So if you can get by there to watch either match, please do so. It should be quite good. The rest of them will come later in the week. I'll let you know as we get closer. College Scholars Bowl is still recruiting players with knowledge of any subject, including history, literature, science, music, current events, mythology, and mathematics. Mr. Matthew West, whose office is down this hall here, the half flight of stairs, go on down past 259, just before you get to 261. His is the office in between those two classrooms. And NASA's Community College Aerospace Scholars Program will be accepting applicants through October the 16th. So you've got 17 days to go, 2.5 weeks. I've got here the emails, contact places, people, whatever. You're certainly welcome to look at this, jot down any of the website addresses that you're interested in. All right. Josh is here, and Bill's here. And Corey's not yet. Hopefully he'll be coming. Okay, we're in Chapter 12, should wrap it up pretty soon. Chapter 12 is vector-valued functions, 12.5, arc length and curvature. We've done the arc length part, now we're going to start the curvature part. And that's where we're beginning today. Any questions before we get started? Okay. All right, curvature. An important use of the arc length parameter, remember that's usually given the symbol S, arc length parameter S, is to find curvature. That's the measure of how sharply a curve bends. Okay? Here's an example, figure 1232 here. The curve is bending much more sharply at P than it is at Q. At P, it's really changing its direction rapidly, and at Q, it's changing direction incredibly slowly. Okay? So P would have a larger curvature than Q. You say that the curvature is greater at P than at Q. Now, you can calculate curvature by calculating the magnitude of the rate of change of the unit tangent vector, capital T. The unit tangent vector, capital T. How fast is that changing? Is it changing? The unit vector is not changing its length at all, so all of its change would be relative to direction, okay? And that's with respect to the arc length S, okay? Now, don't show S here, but remember S, well, it's just arc length. We'll leave it like that. The magnitude of the rate of change of T with respect to the arc length is the curvature of a curve. So basically, the arc length is how far you've gone along the curve, okay? So if you went from P to T1, well, they have, at P, your unit tangent vector is T1. At this next point here, which is just a little bit further up the arc, okay, is at T2. So T2 minus T1 would be basically from this point to that point. And then T2 to T3, then another rather rapid change of things. So the difference there would be, actually it looks like a little bit greater than that. Did the same thing at Q here, quite, maybe my fingers weren't going right. People at home can't see my fingers anyway, but if you were to put T1 and T2 at the same initial point, then the difference there is your change in T, and then put these two at the same point, you would have that. Picture doing the same thing here at Q, and the next point Q, put them together, the change in T would be incredibly small there, because here's your unit tangent vector there, a little bit further on, it's hardly changed. So put them on top of each other, and it would have just a minuscule change in T in those unit tangent vectors, as opposed to these, which are changing really big time. Okay, so that's what we mean. Magnitude of the rate of change of T with respect to the arc length is the curvature of a curve. So let's put that into math speak, okay, into calculus speak here. Let C be a smooth curve, either in the plane or in space, it doesn't matter which, given by R as a function of S, curvature, arc length parameter. R is a function of arc length parameter, okay, where S is the arc length parameter. Then the curvature, remember that's not a particularly easy thing to calculate, but we'll deal with that later, where that is arc length parameter. Then the curvature K is merely the magnitude of the rate of change of the unit tangent vector with respect to that curvature. Very simple formula, okay? But not a particularly easy formula to calculate. Well, and this is just rewriting this in prime notation rather than D by DS notation. So that's it. Really simple formula, not particularly simple to calculate in most cases. Now, let's just get this done. A circle, perfect circle, okay, has the same curvature at any point. Because if it's a circle, then it's not tightening down, otherwise it'd be, or it's not widening out. To be a circle, same curvature everywhere. Moreover, the curvature and the radius of the circle are inversely related to each other. That is, a circle with a large radius, okay, has a very small curvature. Large radius is not curving much at all, okay? But a really small circle, boy, just a little bit of curvature here, you've gone halfway around the circle, okay? So a circle with a circle with a small radius has a large curvature. So they're inversely related. It says here, show that the curvature of a circle of radius R is K is equal to 1 over R. That's what they just told us. They said now to show it. All right. Now, there's, I guess, several ways to approach this, but one would be probably the best way to represent a circle of radius R would be this way. I don't need the folder if you can use it for something else. Right, so
you can just give it to me back in the folder.
Okay, I don't return papers because I have to hang on to them for samples for student writing. I have no need for it. I think you'll need it for another course at some point. Yeah. Save you a little money. Okay. Sorry about that. Before the phone call, it was a previous interruption. I wasn't sure I was going to get any lunch eaten today, but it wasn't too bad. He didn't stay long. Okay. So perhaps the best way to represent a circle is by this representation. R of theta is equal to I kind of hate they're using R, but that's what we usually use. Just get the idea. These R's are not definitely directly related. R cosine theta I plus R sine theta J. Now, sometimes when you see a little r and a vector r, the little r is the magnitude of that vector r, okay? And indeed, that is the case, I think, on this one. Well, no. This is a displacement vector. This is a radius, okay? And they're not related directly. They just use the same letter in the alphabet. So that r is the radius of the circle whose angle is theta, okay? Sorry, it's just because, see, this is a variable r here. That's a constant r there. So don't get those confused. The parameter here is theta, not r, okay? Not little r, okay? Now, that is the simplest way to represent a circle, okay? However, we want it in terms of arc length parameter, S, okay? Well, how is any of this related to S, okay? Well, if you think, sorry, can hardly talk. If you think back to trig days, okay, when we first introduced the arc of a circle, or arc of any curve, but we were talking about circles then, we learned that r was equal to, no, S is equal to r theta. I want to get it written the way I want it to be. Okay, S is equal to r theta. Okay. Remember in trig, the arc length is how far along your, if it's a unit circle, or whatever circle you were dealing with in trig, if that's the arc length, this is the radius, and this is the angle. Okay? What was true about the angle? What kind of units did you better be in? Radians, for certain, because that's how you define a radian. A radian is the ratio of arc length to the radius. That's what a radian is. Okay? So then if theta was equal to S over R, then S is equal to R theta. Okay. Well, then I think we really do want it in the other form. That's the way it looks. So let's do let's rewrite this as theta is equal to S over R. Okay? I'm so sorry. So then you can express R. Now, remember, this R is a constant. In this problem, R is not a variable, it's a constant. S is changing with theta, but R is a fixed constant. Okay? My nose is itching. Okay, so what we have here is R as a function of, well, let's get rid of the theta here and write R times the cosine of S over R I plus R times the sine of S over R J. Okay? So now, remember, these R's are constants. So now you truly have R as a function of S. Okay? It's a pretty ugly S, isn't it? Don't agree with that statement. Okay. Yep, erase it off. Maybe that was best. R as a function of arc length. Of arc length parameter. Okay. Now, this one we can do our R prime then. And if you remember back well, that's t prime. So, but anyway, we'll come back to this. R prime is equal to what then? Remember, R is a constant. Remember this, by the way. Say that again. Yeah. Yeah. So what is the derivative of cosine with respect to s? Minus r sine s over r times chain rule. Remember, s is the variable, r is the constant. Times 1 over r. And that would be your I vector. But this r and that r cancel out. Plus, what would you have here? For the j component. It would be the cosine s over r j. Perfect. Okay? So, there is your r prime, which is, you can take off your velocity vector, you might say. Okay? Now, what is something you note about this? Let me ask you this way. What is the magnitude of the r prime? It's 1, which means not only is that your velocity vector, it's a unit velocity vector. And in what direction is the velocity vector always, or the r prime vector always? Same direction as the, even back in scalar differentiation. Derivative of a function is the tangent. So if this is a unit derivative, this is also then this is also our unit tangent vector in the direction of s, with respect to s. Because r prime is always in the direction of the unit tangent vector. If r prime turns out to be a unit vector, that is the unit tangent vector then. Okay? Now, here's where I meant to turn back to the previous slide. What do we have to do for that then? Take its derivative and then take the magnitude of it. So let's take the derivative of t prime. And what would that be? S is with respect to s, by the way. Anybody? Derivative of minus sine s over r. Got it? Cosine of s over r. Right? Okay, I. That's yes in Navy speak. Okay, next. Help me. Minus 1 over r sine S over R J. Okay? Now, we need to take the magnitude of that T prime. Now, here, probably I shouldn't have put the house stop anymore, because once I take the derivative of a unit vector, it's no longer necessarily a unit vector. So I'll just make that a T with an arrow over it. Even though T is unit vector, T prime is probably not. So the magnitude of this T prime, which is going to give us exactly what we're looking for, which is our curvature K. I think they've already introduced, yeah, they have introduced that. Get out of there. Okay. Is equal to what? Nope, not quite. Square. The square root of the square of these terms. Right? That's the first one. Next. Never a minus because you're squaring it, so that would be 1 over R squared sine squared S over T. S over R. I can't write. I can't read my writing. Okay, so that's the magnitude of it. Now notice what you can factor out. 1 over R squared, but that's in a radical, and when you get out the radical, what do you have? 1 over R times what? 1. So here we have it. Your kappa is equal to 1 over R. That's, I'm sorry, I said kappa. A lot of times, books will use the symbol kappa to represent curvature. This book uses capital K. Now, maybe you might say it's hard to tell a capital K from a kappa. Maybe it is a kappa, but they don't ever say it here, so I just assume they're using it as a K. Usually, kappa doesn't have the serifs and stuff on it. So, that is indeed one over R. And that's true at every point on the circle. There was nothing in here that indicated we were any preferred orientation. You could have been anywhere on the circle, and it'll always be true. All right. Now that's how we did it. They do something maybe just slightly a little different, and that's what I was just looking at and puzzling over. This to me is the most direct way to do it. Let's see what they do. Without loss of generality, you can consider the circle to be located at the origin. Now, I did that without even saying it, so I should have said it. It can be anywhere, but let's just the center be at the origin, then it's pretty simple to go from there. Let xy be any point on the circle, and let S be the length of the arc from R0, which is down here, to xy, which is up here. Okay? And this, if it's centered at the origin, that length is always R, okay? Equal distance from the center to any point on the circle. Okay. By letting theta be the central angle of the circle, which it shows there, okay, then you can represent the circle by R and okay. This is what I was sort of puzzling at before. If you let the circle be centered at the origin, then yeah, these arcs now are related, because that is the magnitude of this arc. So, whereas before I was hem-hawing a bit because I was thinking they were doing it more generally. But if you let it be at the circle, then this indeed is the case. Okay, so they are related in that case, and with that as that, then the R of theta is r cosine theta I plus r sine theta j. Which, by the way, this is your x equal r cosine theta, your y is r sine theta. That's rules for, what do you call it, polar coordinates, you know, how you identify those x's and y's. But even just looking at here, this x is r cosine theta, is that length right there, and y is r sine theta. Good old trick. Where that is not a unit circle, but a r circle, radius r. Okay, so now your parameter is theta. Now using the formula for the length of a circular arc, s equal r theta, you can rewrite r of theta, the vector r of theta, in terms of the arc length parameter, because you can write theta is equal to s over r. And then everywhere you saw a theta up there, put in s over r here. So the r of s now, that's your independent variable. Was theta up here, now it's s, because these r's are constants, okay? Then r of s would be r cosine theta I plus r sine theta. Keep saying theta. R cosine s over r I plus r sine s over r j. The arc length, s is the arc length parameter. That's your variable in this system. The r's are a constant. Okay. So r prime as a function of s, take the derivative of that, and your chain rule part 1 over r here wipes out the r that was in front. So you have minus sine s over r I plus cosine s over r j. And if you just happen to take the absolute value of that, because you were going to try to get the unit tangent vector, and of course you would have to take this vector and divide it by its magnitude. But when you find the magnitude of it, you find out that's simply 1. Okay, because this would be sine squared this plus cosine squared that, that's equal to 1. So if that magnitude of that first derivative is 1, that implies that is indeed the unit tangent vector. Okay? Because it would be the r prime over magnitude of r prime, so that's 1. So this is the unit tangent vector. Okay? That's exactly what it is there. Okay? Why we showed this, but you could. That's where it comes from. Okay, now what is the curvature then? Well, you first have to take the derivative of this, which would be minus 1 over r cosine s over r minus 1 over r sine s over r. This is I, that's j. Take the magnitude of that, and 1 over r squared cosine squared s over r plus 1 over r squared sine squared s over r. Factor out the 1 over r squared. It's in a square root, so that becomes 1 over r, and this is 1, and square root of 1 is 1. For every point on the circle, it didn't matter where you were, for every point, your curvature is equal to 1 over r. Now, as I said, okay, in a circle, maybe it's not too hard to come up with the arc length parameter. Most other curves, not going to be that easy, okay? So, whereas that is the simple formula, curvature is the magnitude of the first derivative of the unit tangent vector with respect to your arc length parameter, because that's, in general, not a very easy thing to do. What you can do here is come up with a couple of easier, so to speak, formulas, at least to calculate. R prime of s is not, okay, for the circle it was easy. The R prime of s in general is not going to be easy yet. So change that from derivative of the magnitude of t prime of S to magnitude of T prime of T over R prime of T. Okay? Now they've got here, this thing is ds dt. Okay? If you remember, this is your velocity, right? The magnitude of velocity is the speed, and the speed is the time rate of change of the sway. Yes. Okay, hold on just a minute. Okay. Now, I was trying to give some rationale for this, and this is it, that your magnitude of velocity vector, that's called the speed, and the speed is the derivative of the arc length parameter. Okay, that is the speed because it's how far you're going divided by the time. Okay, that's how we define speed, and this is that. So this denominator is this, and the numerator is ds dt prime dt times ds dt. But anyway, that works out. So this is exactly, because of this relationship here, that gives you exactly your curvature. Now, how they jump from here to here is yet another issue, unless you go back and see how they did derivative of the unit tangent vector with respect to t. And if you do that, you'll see this is indeed what the representation is. Now, I'll try to go back and show you. I don't think they give you here. Yeah, well, partly. Okay. I'll try to find, this as neatly as possible, but I don't think I'm going to do that. Yeah, I don't want to take any more class time since we just had another interruption. Seems like this is a day for interruptions. But that is the formula. Now, this looks more complicated, right, than the other. The other just said magnitude of the derivative of t with respect to x. Okay? Can you, the magnitude of that. Can you get any simpler than that? The thing is, to get this in function of t is not an easy thing at all. I mean, to get it as a function of s is not an easy thing at all. So this is more complicated looking here, but guess what? You're always given r of t. And then finding the derivative of r of t is very straightforward. And then the magnitude of that is pretty straightforward. Okay? And once you've got that, you can just cube that, whatever. Okay. Up here, and this comes from previous formulas that we have, this could be written as r prime, which is, again, you've already calculated it here, so r prime dot cross with r double prime. Well, you've done that. That's a really easy thing to get. So this cross product is pretty easy. So you do the cross product, find this magnitude, do the first derivative's magnitude, and cube it. And there it is. The calculations here are easy. The steps are easy. It looks more complicated. It is a little bit more, but it's not nearly as bad as trying to get everything in terms of S. Okay, that really becomes a pain in somebody's part. Okay. The first formula implies that the curvature is the ratio of the rate of change of the unit tangent vector to the rate of change of the arc length, which is, pretty much, I mean, that's basically the definition of it. see that this is reasonable, that delta B be a small number, then, oh boy, they're doing this. Oh boy. The denominator here, they're doing dSdt. The numerator, they're not doing the magnitude of it, they're doing d prime, which is, almost feels like that's not fair, okay, to deal with the magnitude down here, but not the magnitude up there. But, that being said, this thing is your unit tangent vector at some t plus delta t minus the unit tangent vector at t divided by delta t. And this is s of t plus delta t minus s of t over delta t. What's that?
That looks fun.
Yeah, it does. It really does. What in the world are they doing next? Since the delta t's cancel out, yeah, that's just a small number, not a differential anymore, but just a very small number. Those cancel out, so that leaves you this and that. And this is just change of t over change of s. Which is I don't know, why are they hanging you there? The magnitude of that would be kappa. But they're not doing that at this point. Maybe they'll do it on the next. No, okay. No, that's just the change of your unit tangent vector with respect to s. But remember, that's what we first said your curvature is related to, is how much your unit tangent vector is changing with respect to your unit, to your arc length parameter. Okay? In other words, as if all those words weren't confusing enough, for a given delta s, the greater the length of delta t, the more the curve bends at t. And this is what I was trying to show before, waving my arms there as they show it. Here's your first point t, okay? And there's your unit tangent vector at t. Unit length, tangent to the curve there, okay? You go up some little delta s, and now your original t was here. You just translated that here. Your new t of t plus delta t is here, tangent there. Your change of t is the difference between those when you put it at the common initial point. Then that's your delta t. Well, then this delta t per delta s, that is your rate at which unit tangent vector is changing with respect to that. That's your curvature. Okay. Now, when it's over here, that's a fairly small delta t. Okay. And the delta t divided by delta s, which is a bit longer, it even makes that ratio a little bit smaller because you're dividing one number by a number fairly larger than it. Okay? But over here where the curvature is great, here's your t at t. Same delta s here. That looks like it might be a little shorter, but it's supposedly the same delta s. And then here was your previous delta t of t. Here's your new t of t. Look at that change. Not this little bit, but that bit. Okay. Now, this thing divided by there is much larger than 1. This one was smaller than 1. This one was larger than 1. So where it bends more rapidly, that gives you a greater curvature. And that's exactly what we said before. Broader the more gentle the turn, the smaller the curvature, the more rapidly it's turning, that's a greater curvature. All right. Now, we're ready for example 5. Find the curvature of the curve given by r of t is equal to 2ti plus t squared j minus 1/3 t cubed k. Now, thinking back about what your kappa is, that's what we're looking for. Oh, let's write it below it. What is curvature, kappa? Oh, I like to call it kappa. This book calls it capital K. Whatever you want to call it. Fred, I don't care. Okay? What is its definition? Oops, that one. You can go for the intermediate one, but really the easiest one to calculate is that one. R prime of t cross R double prime of t magnitude divided by magnitude of R prime of t cubed. Oops, wrong one there. Okay. Magnitude of R prime of t crossed R double prime of t divided by magnitude of R prime of t cubed. Okay? So what you reckon you're going to have to do first? Take a derivative. So let's do your R prime of t first. And what would that be? 2i plus 2tj minus t squared k. Perfect. Now what do you want to do next? You got two more steps to do.
Just go ahead and get the
Next derivative, second derivative. R double prime of t is is it?
well,
Derivative.
it's not.
Yeah, 0i, because derivative of 2 is 0. Okay?
It's plus 2j
2j
minus 2k.
to tk. Got it. Okay? Now, what do you want to do next? You got a couple of options.
I did the cross product.
Cross product next. That's pretty easy to do, I think. Let's do it. R prime of t cross R double prime of t would be I, J, K, I, J. That's how I do it. Then the one that's listed first next. 2t minus t squared, 2 and 2t. And then the one listed second, 0, 2, minus 2t, 0, 2. All right, so let's do it. What the first diagonal will give you? Negative 4t squared, I, 0j, plus, okay, now do this one, the k one, 4k.
I must have wrote those down wrong.
I hope I did it right. You just repeat the first two columns for every row you do.
Oh, I did pay.
Okay. Now, all right, to erase my construction lines here, because I'm afraid they'll just block your vision of what's coming next. Okay, now let's do our down, or I guess you call these your up diagonals. What's the first one? 0k. Your next one? Yeah, plus 2t squared I. Because you're doing up diagonal, those are always negative. And this one would then be plus 4tj, right? All right, combine like representations here, and I think you have a minus 2t squared I plus 4tj plus 4k. Got them all? I think so. Okay. Now we need to do the magnitude of that. And what would that be? 4t to the fourth plus, what did you say? 16. Okay, I got you now. I thought I heard 6, and I thought, how did he get that? Okay, 16t squared, got it.
And then plus 16.
16. All right. Now, just looking at that, I see something I can deal with.
I would take the 4 out of all.
Take a 4 out, and 4 is the square root of?
Wait, sorry.
4 is the square root of? Or the square root of 4 is?
2.
2, yeah, that's what I meant to say. So this would be 2 times the square root of t to the fourth plus 4t squared plus 4. Now, does that look anything familiar? T squared plus 2 squared. And since that's squared, it is and take it out of there, it'd be 2 times t squared plus 2. Right? Which you could say is 2t squared plus 4, but let's just leave it like that for now. So there's your numerator. What else do you need to do?
You got to get the magnitude of just.
Yeah, the magnitude of r prime, and then you're going to cube it. So let's first do the magnitude of r prime. And here's your r prime. So its magnitude would be the square root of 4 plus 4t squared. More like, yeah, plus t to the fourth. Okay, I got lost there in which line I was looking at. Okay, now do very much, and that is again the square root of t squared plus 2, right? Or t squared plus 2 is the square root of that thing. Okay, but you're going to cube that then, r prime cubed. So, what is our curvature? K is equal to 2 times t squared plus 2 divided by t squared plus 2 cubed. Well, one of these will cancel out there. And you're left with 2 over t squared plus 2 squared. Goodness gracious. Oh my. Okay. Now, that's what they're looking for, and that should be the answer. But let's see what that's telling us. When t is incredibly small, maybe even getting to 0, then this would be 1/2, right? T is 0, that would be 2 over 4.
Yes.
Okay, that would be 1/2. That's the larger curvature it's going to get. Because any t, whether positive or negative, your denominator, beyond that, this gets bigger. So you got a bigger number here, squaring it is even bigger. So you're dividing 2 by a larger and larger number, which means it's getting very much smaller. So in the long run, the the curvature acts like it's going to zero. Of course, it won't ever be perfectly zero, but that's where it's heading. But it's 1/2 at the t equals 0. Okay. Okay. And that's the same thing they got. So let's us see how they got it and see if there's any major difference. Okay. It is not apparent, they say, whether this parameter represents arc length. I would say almost definitely it's not. Okay. So you should use the formula t prime over magnitude of t prime over magnitude of r prime, which I don't find as all that easy to do, because what you have to do, you have to first get r prime, then you have to divide by the magnitude of r prime, then that is your t, and then you have to take the derivative of that, and then you have to divide by its magnitude and divide that by the one you've already calculated. Yeah. But that's how they do it, okay? Your r prime of t, just like we got, was 2i plus 2tj plus minus t squared k. The magnitude of the r prime that you're going to need there is square root of 4 plus 4t squared plus 4. T to the 4th. Which turns out being t squared plus 2, which y'all noted earlier. Okay? Now, leave that alone for now and go back to your r prime of t, and your t of t is going to be the r prime of t from here divided by magnitude of r prime of t from there, and that gives you 2i plus 2tj minus t squared k over t squared plus 2. Okay? Now you've got to take a derivative of that with respect to t. Not my favorite thing to do. Okay? And they do it. Oh my goodness. They are serious about that. So it's the low d high minus high, there's a high, d low, over low squared, low. Okay? Yeah, this is my favorite way to do it. Oh my goodness gracious. You have this times 2j, so 2t squared plus 4j. And over here you have a minus 4t squared j. So that gives you, yeah, you can do all this. Yeah, you can do all that. It'll work out, I promise, okay? Let's do the i's first, because there's only one of them. Okay, minus 4ti, got it. Plus, and like I said before, when we're doing the j part, you got a 4 from here, and then you got a plus 2t squared and a minus 4t squared, plus 2t squared minus 4t, minus 2t squared j, and then the k part is going to be minus 2t cubed k minus 4t k minus 2t squared k no, 2t cubed k. So that one and this one will cancel out, and that leaves just that one, which is minus 4t k. Yes, fine, okay, over that thing squared. Okay, aren't you glad we didn't do it this way? Well, why are we having to now? Okay. Now you do the magnitude of all that. That's your t prime. The magnitude of that would then be the magnitude. Okay. First, this. Huh?
Why did they leave the 16t squared minus 6? Oh, never mind.
Yeah. They just left this down here because that's not part of that part. So just leave that down here rather than squaring and then taking the square root of it. So just leave that out. Okay. So this will be a 16t squared plus, and now you have to do square the binomial, which would be 16 minus twice 8 is 16, so that would be minus 16t squared. And then when you square this, you get plus 4t fourth, and then you square that and you get plus 16t squared. All right, so one of these goes out, leaving you just one. So you got 16 plus 16t squared plus 4t to the fourth, and then that's under a square root, and then factor out the 4 from that, which when it comes outside the radical is a 2, and what you have left is just that t squared plus 2. We did it before. Now you got one of these up here, 2 of them down here, so this is 2 over t squared plus 2. I surely like the r prime, r double prime, cross product, magnitude, and then divide by. It's just a lot easier in most cases. Maybe in a few cases this will end up being used, but I kind of doubt it. So it's 2 over t squared plus 2. Okay. And they say that's the length of t prime squared. Yeah, that's what this is. The magnitude of t prime squared. Magnitude of t prime, sorry. All right. And so the kappa is then that magnitude divided by, or I keep saying kappa, k, capital K, is that t prime we just calculated divided by r prime, which magnitude of r prime, which was, yeah, it's already on the previous slide. There was magnitude of t squared plus 2. So it was this thing divided by another t squared plus 2. So that makes it t squared plus 2 squared. That's your curvature. And they don't do anything else about it. I thought they would at least, try to give you a warm fuzzy what that was representing. All right, so that's their example 5. The next theorem presents a formula for calculating curvature of a plane curve given by y is equal to f of x. All right. Now, plane curve, y is equal to f of x. Notice there's no vectors in this, okay? But the curvature then at any point xy is your y double prime, the absolute value of the y double prime, divided by 1 plus y prime squared raised to the 3/2 power. Yes, so that makes a lot of sense, doesn't it? And I frankly can't think of any really easy way to remind you, let you know what this is leading up to it. But if you go back and think about it, I believe your arc length wound up with something to the 3/2 power in the denominator. And remember, if this is to the 1/2 here, that was a lot like what your arc length looked like. The square root of 1 plus y prime squared. That was what arc length was. Now you're going to take that and cube it, which is what we did earlier, and that divides into the magnitude of r double prime. think of any easy way to remember it. Just, there it is. Okay. But notice there's no vectors involved with this. And yet you can talk about curvature. They do have the proof there that you can follow through, and it's probably not all that terribly hard to do. Because y is equal to f of x, so your I component is x, your j component is f of x. And then you really don't have a z component because this is a two-dimensional graph. I believe they told that. So there is no z involved. And then you go on from there, and you know, a few of the things I was talking about, they do show up here. And take the derivative of what I just said, you know, use that other formula, you wind up with this. Now, that being said, middle of page 850 is sort of a new, quite a new concept, but looking at things slightly different. Let C be a curve with curvature K, keep on to call it kappa, at some point P. The circle that passes through that same point P with a radius of 1 over K, okay, is called the circle of curvature. When the circle lies on the concave side of the curve and shares that common tangent line with the curve at P, the radius of that circle is called the radius of curvature at P. And the center of the circle is called the center of curvature from that point P. Remember, they put it on the inside of the curve. Now, the circle of curvature gives you a nice way to estimate the curvature K at any point P on the curve graphically. Using a compass, which I'm sure we all still have, don't we? You can sketch a circle that lies against the concave side of the curve at point P, as shown here. Here is your curve of interest, okay? There's your C. And you pick that point P, okay? And you get your compass and you try to form as large a circle as you can that touches at P here, but doesn't extend outside the curve, okay? If the circle has a radius r, then you can estimate the curvature of the curve, C, to be also 1 over r. Okay. Key here, who still has a compass? I haven't used one in a long time. Oh, yeah, okay. So you can tell what direction you're going. Okay. See, he's so young, he doesn't even know what I'm talking about. Okay, got it. All right. I think we're ready for example 6, maybe. Ooh, wow. Other text, I'm pretty sure, rather than calling this, I'll need to go back and check, but I think they call this an osculating circle. I believe I remember that from another code. This one just calls it the circle of curvature. I like that a lot better than osculating because I have to remember how to spell osculating, and that's not easy, okay? And so everything is just circle of curvature or radius of curvature, and that's approximately equal. Oh, and the center being the center of curvature. Just makes it a lot easier. Okay, find the curvature of a parabola given by y is equal to x minus 1/4 x squared at x equal 2. Sketch the circle of curvature at 2, 1. Okay, let's first do the parabola. Which way is this parabola opening, up or down? Down, okay, because the quadratic term is negative. Yeah. So let's get our axes here somewhere and find a few points. When x is equal to 0, y is equal to 0. Well, I didn't need it there, did I? Well, we'll see. Okay. When x is equal to 1, y is equal to 3/4, I think. Somewhere about there. When x is equal to 2, x equal 2, that would be, 1. Okay. When x is equal to 3, that would be 3 minus 9/4, which would be 12/4 minus 3/4 again. Okay, so here we're down to 3/4 again. Looks like that's going to be part of your circle there, and 2, 1, sure enough, that looks like the vertex of your parabola, doesn't it? Okay, so we're asked for the curvature of the parabola given by that, at x equal 2. Okay, now, they don't say whether to do it using your circle of curvature or they just say find the curvature. So I think what we're supposed to do is go back and use this formula here, because notice here we have a y is equal to the function of x. We don't have a vector equation, so we just have that. So let's go back here and get our thing. Magnitude of y prime over 1 plus y prime squared, y double prime on that, y prime squared to the 3/2 power. Okay, so curvature is equal to magnitude y double prime if it's not a vector, you don't put a second bar. Okay. Okay. 1 plus f prime, let's not mix them up, let's call it y prime, y prime squared to the 3/2 power. Okay, so what you reckon we got to do first? Second? Okay, y prime is equal to 1 minus 1/2 x. Okay, and y double prime is equal to negative 1/2. Okay, so your curvature is the magnitude of that second derivative at the point 2, 1. Well, that's just 1/2. Okay, now divided by 1 plus 1 minus 1/2 x squared. And that whole thing will then be to the 3/2 power. Okay? Now, since we're only interested in the curvature of the parabola at x equal 2, it's all right to go on and plug that in now. Don't square your binomial, add 1 to it, and then take the 3/2 power of it, and then plug in. Let's just plug in now, okay? Okay, this will be 1/2 over 1 plus, let's see, I'll get my parentheses right, and this will be 1 minus 1/2 and your x is 2, so that'd be 1. So yeah, that comes out being, that's the 3/2. Boy, that's ugly. Okay, let's see if we can do it a little bit better. 3/2, so 1 to the 3/2 is still 1. So this is just 1/2. So there's the curvature. Now it says sketch the circle of curvature at 2, 1. Now what do you need to do before you can sketch a circle? Radius, okay? And if the curvature is 1/2, what is your radius? Two, exactly. Radius is 2. Okay? So if your radius is 2, that's your vertex up here. Go down 1, 2. So your center is going to be at 2, -1. And then your circle will go to there, to there, and to there. This is a pretty ugly sketch. Okay, something like that. And you see your parabola does something like this. So for a little bit of the way there, they probably do come very close to each other. Okay? Mine is not very pretty at all. Okay? Okay. I think that's all they wanted you to do. Let's see. Okay. Curvature at 2 is as follows. First, your y prime is 1 minus x/2, just like y'all got. Okay. Then y double prime was minus 1/2, just like you got. Okay. Now your y prime at 2 would then be 0. Y prime at 2, y double prime at 2 is always minus 1/2. It's not changing any. Okay. Your curvature is the magnitude of your second derivative. Second derivative is minus 1/2, so its absolute value would be 1/2. And this thing that the y prime is 0. 0 squared is 0. 1 plus 0 is 0. 0 to the 3/2 is, 1 to the 3/2 is 1. So this would be y double prime over 1.
Now, since you have double primes minus 1/2, and the curvature is the 1/2, is there a connection between those two? Or it just came out that way?
Well, because this denominator is 1, it came out that way. The reason they do the absolute value here, I've already erased mine. In a minute, when they show this, I'll give you sort of a quick and dirty on why they did that. Okay, because the curvature at P21, and I don't know, did we ever do that? Yeah, I don't think we did. They just told you at x = 2, and then they said at this. We graphed it and saw that was true, and we did, because that's how we graphed it. When you put 2 in here, you get, this becomes 1. Yeah, this is 2, and that's 1, so that gives you 1 there. Yeah, we did that. We didn't do it, well, we did it sort of explicitly, but we're doing it when we're plotting our curve. So yeah, we've done that. So because the curvature at P21 is 1/2, it follows that the radius of the circle curvature at that point is 2. Okay? So the center of the curvature is 2, -1, because it's 1 radius below that, and it's shown here. Now, here's what I was going to show you. If you had used the -1/2, you would have had the circle up here. And that wouldn't have made a lot of sense because it's outside. So by choosing absolute value, that always puts you inside the curve. Okay. But that's the relationship to the -1/2. If you had used that, your circle would have been up there, which would have been a circle with that curvature at that radius, but not with the absolute value. Okay. So we didn't want that. So I'll erase that. But, okay. So there you have it. Okay. Now, you see their circle did a lot better job hanging with the parabola for a lot longer than mine did. Mine was such an ugly circle. There's the curve, and this does a really good job of following that curve for quite a ways. It's not exact, never will be. It is exact right there. They start deviating ever so slightly, but a very slow deviation until you get down to about here or here, and you finally start seeing some spread from there. That's just because of the thickness of your lines and stuff like that. Okay. In the figure, note that the curve has the greatest curvature at P. Anything later is going to get smaller curvature, being a bigger circle. If you're going to Q here, then that circle would have been much bigger. Now that circle, if you drew that circle, it's going to enclose some of this over here because I'm pretty sure it would. Now, may not. It may not quite incorporate into that, but it comes pretty close to it. So here is then they've left out a lot of verbiage here. Let me throw in a little bit. Okay. Okay. Right here in the book, after they say this statement, in this figure it shows the greatest curvature is at P. The next statement in the book says, try showing that the curvature at Q4, 0, that one over there, the one I was pointing at, is 1 over 2 to the 5/2 power, which is about 0.177. So that would have been a bit more to do. But the verbiage at the top of the next page, before you get to this theorem, says arc length and curvature are closely related to tangential and normal components of acceleration. The tangential component of acceleration is the rate of change of speed, which in turn is the rate of change of arc length. The component is negative as the moving object slows down, positive as it speeds up, regardless of whether the object is turning or traveling in a straight line. So tangential component is solely a function of the arc length and is independent of the curvature. Okay. So the tangential component is solely a function of the arc length and is independent of curvature. Yeah. Tangent doesn't care what the curvature is doing, it's just going to point there out. Okay. On the other hand, the normal component of the acceleration is a function of both the speed and the curvature. So this is what this component measures the acceleration acting perpendicular to the direction of motion to see why the normal component is affected both by speed and curvature. Imagine you're driving a car around a turn, and we don't have this picture here, but you see it in the book. When your speed is high and the turn is sharp, you feel yourself thrown against the car door. By lowering your speed or taking a more gentle turn, you're able to lessen that sideways thrust. They talk about centripetal acceleration, though they don't say it. But anyway, here is the theorem that's relating that verbiage. If R of t is the position vector for a smooth curve C, then the acceleration vector is given by A of t, what we used to call A sub t, now they're calling the A sub t, d, the second derivative of arc length parameter as a function of time, second derivative with respect to time. Okay, so that's only depending on your speed, basically, because ds dt is your speed, that is the rate at which your speed is changing, that's your acceleration. Speed component of the acceleration, that's your tangential component. Whereas then your normal vector is your curvature times the speed squared, times your unit normal vector, where k is the curvature of C and ds dt is the speed. So that's the speed, that's the first derivative of the speed, this is your curvature. So can't think of anything else to say about it, but and that's why, and this was what was coming back to my mind when we had that r prime of t cubed in the denominator. That reminded me back when we were doing the accelerations. Well, I can't lay my hands on it now. Actually, it was before that, I guess. But you wound up with the denominator being, I don't see it now. Never mind. Well, if it pops back up, I'll point it out to you then. Okay. But that's the tangential component, only a function of speed, the normal component, function of the curvature, which is the dealing with the path and the speed then too, speed squared in fact. Okay. So, example 7. How are we doing on time? Okay, whoa. Is that right? 5 minutes. Huh?
5 minutes.
5 minutes, okay. I lost. Yeah, okay, right. We go to 55, okay. I was thinking we went to 45. I thought we went over. No. Okay, find A of t and A sub n for the curve given by this. Okay? I don't think they want you to do it the way we did it before. Let's do it this way. Where would you begin? Take a derivative. Always a good idea. R prime of t is, we've seen this before, haven't we? 2i, 2tj, k. We've seen that. And since we've seen it, we have already calculated, so let's just go back to that one. This was example 5. Okay? This will save us a little bit of effort here. I think all that we can get out of that, the way we did it, we could get a little bit more, but the way they did it, their curvature was 2 over t squared plus 2 squared. Okay. Save us having to do all that again. All right. Now, all right. So you certainly had to do R. R prime. Okay? And we did do the second part that they didn't do. When you do R prime of t, the magnitude of R prime of t, remember what that gave us? Square root of 4 plus 4t squared plus t to the fourth, which we interpreted to be 2 plus t squared, 2 plus t squared, right? Remember we did that? Okay. All right. Now, I don't know if you remember this part. That this thing here, this is underneath on page 859, immediately under the theorem there, because R prime of t, the magnitude of R prime of t, this is equal to ds dt. And if that's equal to that, that means this is equal to that, okay? Because those are the same thing. All right. So we've got our second piece of information, though we didn't, the book didn't explicitly say this before, but we did, I think. I hope we did. It seems like we did. I've erased my work then. Okay. So, with that done, find a sub t. Well, what was a sub t? d2s dt squared. Okay? So, a sub t, now I guess we should be putting that as a vector, unit vector at that. This is equal to d2s dt squared, which is equal to, take a derivative of that, and what do you get? 2t. So there's your a sub t. Your a sub n, unit normal vector, go back here, and that's your curvature times your speed squared, basically, okay? Just to keep from, yeah, well, that's what they call it here, it's c squared, okay? Well, that's your speed, so we're going to square that. The curvature is 2 times t squared plus 2 squared times speed squared is 2 plus t squared squared, which is exactly that. So your acceleration in the normal direction is 2. Now that's a little bit easier than doing the way we did before, okay? In fact, a lot easier in this case. Obviously, they just happen to work out. So your a sub t is 2t, your a sub n is simply 2. And that's what they got here too. Just as straightforwardly. A sub t is 2t, and a sub n is 2. All right. Now I think we're out of time, aren't we? Yep. Sorry about that. Let's quickly see how they did it, because I talked too long on that. Okay. From example 5, we knew that r prime of t, magnitude of that was ds dt, and that was t squared plus 2, and the kappa, or k, curvature is 2 over that. So a sub t is the first derivative of that, which is just 2t, and the a sub n is k times the square of that. Well, k is 2 over that. The square of that is t squared plus 2 squared, and that just gave you 2. All right. We'll start next time at the application. And once upon a time, I had a pencil out, and I must have put it back in the drawer. Okay. So we'll start there, erase that. Okay. Let's see what homework exercises we dug up. Oh, we came so close to finishing. Okay. You can do any of the odds 3 through 7. They're all at Calc Chat. Number 9's at Calc Chat. 11 through 15 are at Calc Chat. 13's at Calc View. 17's at Calc Chat. 19 or 21 are both at Calc Chat. 21's at Calc View. 23 to 27 are at Calc Chat. 29 through 35 are at Calc Chat. 33's at Calc View. 37 and 39 are at Calc Chat. I think you can do 41 through, let's see, what's the next? 41 through 47, they're all at Calc Chat. 43's at Calc View. 49 through 53 are at Calc Chat. 55 and 57 are at Calc Chat. 59, you can explore doing that. That should be at Calc Chat. And we'll stop there and pick up the rest of those next time. Okay. And I just discovered these. I need to move back, but I'll do that later. All right, any